Hello, welcome back. So finally, we are out of the realm of formal groups. They'll come back still, but they'll come back to help us to study elliptic curves over local fields. So now we are going to think of elliptic curves over local fields. So here K is going to be a local field. Remember that for all intents and purposes, if you think of QP, when we think of local field, that's exactly what I have in my mind. Okay, but we have a local field. Those come with valuation, so this is complete. This page doesn't want to stay up. Complete with respect to discrete evaluation new. We have R. It's ring of integers. So the ring of integers are elements with positive or zero valuation. We have R cross. This is the unit group. The unit group are those elements with the valuation exactly 0. Then we have the maximal ideal of the local field. Those are elements with positive valuation. We have what we call a uniformizer. Uniformizer for R. Remember, we had that notation, a uniformizer for a function on the function field was a function that vanished to order 1. So it's sort of like that. It's an element where the valuation is this element actually generates the maximal ideal. So the uniformizer is an element such that pi times R is the entire maximal ideal, and one can, if you want, normalize the valuation so that nu of pi is 1. You either normalize to nu of p being the characteristic of the residue field, to p being 1 or pi being 1. I typically normalize, so pi is the one with valuation 1. Okay. And yeah, the residue field. So this is the residue field of my local field, and P is the characteristic of the residue field. Okay, so we want to talk about elliptic curves over local fields. So the first thing to do is define minimal Weierstrass equations. So remember, so if I have an elliptic curve over a local field, what that means is that there is going to be a Weierstrass model for my elliptic curve. I do want to think about the long Weierstrass models. You'll see in a moment why. Even if the characteristic of K is 0, I still want a long Weierstrass model in this case, because I want to find, by minimal Weierstrass model, what I want is to find sort of like the best model possible for this elliptic curve. So recall that I can change variables. If I change variables by sending x to x over u squared and y to y over u cubed, then the way the coefficients change in my new model is that ai goes to u to the I ai, which is what we would call now my new coefficient ai prime. The discriminant of the model changes by a power of 12 and that would be my new discriminant, and my C4 coefficient changes by a power of 4. That would be my new C4. Okay. But recall also that if I changed by more generally, if I change by, remember that the more general changes of variables that change the Weierstrass model, but it keeps a Weierstrass model, are all of the form. We proved this actually was a consequence of Riemann-Roch by comparing some spaces. Then the discriminant still changes by a power of 12 of this constant u that is featured in the change of variables, and the C4 still changes exactly by a power of 4. Okay, so in both cases, the discriminant and C4 change by the same powers. Okay, so now what I can do is consider all possible Weierstrass equations for my model, and then see which one has, I want integer coefficients, so I want the coefficients to be in R, to be the coefficients to be in ZP. If you're thinking of the p-adics, I want p-adic integers as coefficients, and I want my discriminant to be the smallest possible. Okay, so that is how we define a minimal Weierstrass model. So let E over K be an elliptic curve, a Weierstrass equation as above is called a minimal Weierstrass equation for E at nu if the valuation of the discriminant is minimal, subject to the condition that the coefficients, I want them to be integers. Okay, first of all, if I have a Weierstrass model and there are denominators, I can always change a variable with one of those, the basic ones here. With this, you see, I can always, if there are denominators, take u to be the least common multiple of all denominators, and then this is going to take care of all the denominators. I'm going to have a model that has integer coefficients, and then amongst all those, I want the one with the discriminant being of lowest valuation at nu. Okay, the value of the discriminant in that case is the or the oops. Such discriminant is called the minimal discriminant, and that's it. All right. Here's one remark is that so if the coefficients are already in R and the discriminant is in R and C4 is in R, if not minimal, if delta is not already minimal, then there is a change of variables sending x, y to u square x, u cube y, one of those, with the new discriminant that is minimal. So in particular, it only changes by multiples of 12. The valuation of the discriminant, the valuation of the discriminant can only change in multiples of 12. So in particular, if you already have that the coefficients are integral and the valuation with the discriminant then integral, the discriminant is a function of the coefficient. So if the coefficients are integral, then the discriminant is integral. And if the valuation is already less than 12, then the equation is minimal. Okay. Similarly, C4 changes by values of by multiples of 4. The valuation of C4 changes by multiples of 4. So if the coefficients are integral and the valuation of C4 is already less than 4, then the equation is minimal. Okay, so let me give you a couple of examples. By the way, if the characteristic of K is not 2 or 3, the converse also holds. Okay, that if the equation is minimal, then the valuations have to be less than 4. If less than 4, less than 12, the minimality at 2 and 3 can be quite tricky sometimes. Okay. So let's give some examples. So why are we bothered? Why are we bothering about this? The very first example is that if you have an elliptic curve like this, for example, plus 5 to the 6, this elliptic curve. So what's going to happen is that we are going to think of elliptic curves over Q, say. But then we want to know where these elliptic curves have bad reduction. We'll talk about reduction probably next time now. We want to reduce these equations modulo primes and see where there is good reduction, that I get more elliptic curves over FP once I reduce, or no elliptic curve because there is a bad reduction in the reduction, the reduced curve that has a cusp of some sort. So here, if I reduce modulo 5, then I get this model is bad because I get this over F5, right? Which is singular. But what happened is that I picked a bad model for this elliptic curve because I could have just changed my coefficients. If you do a change of variables by taking u here to be 5, then this is, let me put primes, plus 1 over Q, and now mod 5, y squared equals x prime cubed plus 1 over f5 is non-singular. Okay, so we want to find out what primes I can reduce my elliptic curve at and still get some nice elliptic curve in the reduction, and primes that are there that are bad reduction, but they should not be there just because I picked a bad model for my elliptic curve. Those primes, I don't want to see them in my discriminant. Okay, so if you compute the discriminant of both forms, of this form and this form, they differ by a power of 5. There is a power of 5 here that did not need to be. There's a 12th power of 5 in the discriminant there that is not present here. Okay. Let me give you then some other example to check minimality. So if I take my elliptic curve, y squared plus xy plus y equals x cubed plus x squared plus 22x minus 9. By the way, the reason why I wanted even in characteristic, not 2 and 3, even in characteristic 0, I want my my models to be long Weierstrass, is that by forcing a model to be short Weierstrass, I might be introducing bad primes that should not be there. So sometimes you have a model in short Weierstrass that has an equivalent model in long Weierstrass that some prime that was bad in the short is actually good in the long Weierstrass. So there is sometimes the discriminant, the evaluation of the discriminant can be reduced by changing to a long Weierstrass equation. In this particular case, the discriminant is precisely minus 2 to the 15 plus 5 squared. Okay, so it looks like it may be, oops, that's not plus, this is times. Okay, so there is a power of 2, there's a high power of 2 there, and you might think like maybe this elliptic curve has maybe it's not minimal at 2, and I can reduce it somehow, can change variables to get rid of that power of 2, reduce it to something like 2 to the 3 times 5 squared. And it turns out that no, because C4, if you compute C4 also, this is minus 5 times 211. Since the valuation at 2, so this is minimal for all primes. So so notice that it's minimal for p bigger than 3 because the valuation, actually what it is minimal for all primes simply because the valuation at p of C4 is it is 0 if p is not 5 or 211, and 1 if p is 5 or 211. It is less than 4 in all cases. So it is minimal, and that's the smallest smallest in terms of valuations discriminant that you can find among all the models of this elliptic curve. Okay, so you cannot do better at 2 than this, and you have to live with a discriminant that has a phi power of 2 in this particular elliptic curve, meaning that 2 is a intrinsic bad prime that you cannot remove. Okay, we'll continue next time. I'll give you some other example next time where I can remove some bad primes by changing models around. So we'll continue with elliptic curves for local fields in the next lecture. All right, bye.